Hello. So this is our video that we missed at today's lesson. It's going to be all about inverse functions. Inverse functions. That's what we missed today. All right. So let's look at it. Definition. So first, before we can talk about that, we got to talk about one-to-one functions. So a function f with domain D and range R is said to be one-to-one, provided that either of the following equivalent conditions are satisfied. So either whenever A does not equal B in the domain, then f of A does not equal f of B in the range. So if you have two values that are not equal in the domain, right, then essentially when you take f, they should be pointing to two different things in the range. That's what it's saying. Right? That's going to be one-to-one. Or alternatively, we could say if f of A does equal f of B in the range, then A has to equal B in the domain. That's kind of saying the same thing, but if you notice, right? So if we have f of A is f of B, so A and B are pointing to the same thing, right? A and B pointing to the same thing, then it only makes sense for it to be one-to-one if A and B actually are the same thing, right? So it would be closer to A and B are the same thing. And so it's just one thing pointing to each other, right? Notice this is one-to-one, right? Everything is only pointing to one individual thing. So if two things are pointing to it, that's not one-to-one anymore, right? So that is not one-to-one. So we can talk algebraically what that actually means. And I will let you know that typically rule number 2 is the one that we use for this one-to-one definition. So if we look, determine whether a function is one-to-one. So let's say f of x is 3x plus 2. So essentially what we do is we just say, all right, whenever f of a equals f of b. So let's assume f of a equals f of b. And if it's one-to-one, we want to show that A equals B. So that's eventually what hopefully we'll show if it ends up being one-to-one. So what is f of A? Well, since f of x is 3x plus 2, f of A will be 3a plus 2. f of b will be 3b plus 2. So we can subtract 2 to both sides, get 3a equals 3b, divide by 3, a is b, which is exactly what we wanted to show. Thus, we have shown one-to-one. Let's do another example. So g of x equals the square root of 2. So once again, we assume g of a equals g of b, right? We can substitute that. So to go further, we can square both sides. So we get a plus 2 equals b plus 2. And then subtract 2, a equals b. All right, we got what we wanted again. So one-to-one. Oop, that was weird. All right, let's try this last one. So f of x, or h of x, excuse me, is x squared plus 3. So we can do f of a, or h of a equals h of b. So a squared minus 3 is b squared minus 3. A squared is b squared. And so what a lot of y'all are going to think is, oh, you take the square root, so then a equals b. And we're done. But that is not correct. So take a second and just think, what's wrong with that? What's wrong? Well, remember, anytime you take the square root, you got to take plus or minus. So it's plus or minus b, right? A is plus or minus b, which means A either equals plus b or minus b, right? So since A could be positive b or negative b, it could be the case that A does not equal b. Thus, it is not one-to-one. Now, side note, some of y'all might say, well, hold on a second, we did square root of both sides. How come it's not plus or minus A equals plus or minus b? Well, you end up seeing, if we list out all those possibilities, you end up seeing that it basically just simplifies down to this. So if we had plus or minus A is plus or minus B, right? Then that means either A equals B, positive A equals negative B, negative a equals positive b, or negative a equals negative b. But if you notice for part 3 and 4, we could just multiply 3 by negative 1 to both sides, right? And we get a is negative b, which is what number 2 was. For number 4, we can multiply everything by negative 1 and get a equals b, which again is what 1 was. So we can just kind of simplify that to just say a equals plus or minus b, call it a day. But we see that since we did not conclude that a equals b, right? So we can't conclude that it's 1-to-1. It's actually not 1-to-1. Another way to think about that. So we can do not. We can prove it's not 1-to-1 using the first definition. So if we go back to the first definition, whenever a does not equal b, then their functions, when you plug it into the function, it can't equal the same thing. So if we have x squared equals 3, right? Well, what's two numbers you could plug in to get the same thing? Since we have this square, you can see positive and negative answers are going to give you the exact same thing, right? So notice negative 1 does not equal 1. However, h of negative 1 equals h of 1, right? So h of negative 1 is going to be negative 1 squared minus 3, 1 squared minus 3, which ends up just being negative 2 on both. But remember, if it was 1, so basically, right, if we draw that, positive 1, negative 1, they both end up going to the same answer, which, as we said, was not 1-to-1. So another way you can think about it. So let's look at the horizontal line test. So that was the definition of 1-to-1 algebraically. We could also talk about it 1-to-1 graphically. So this is another way we could do it. A function f is 1-to-1 if and only if every horizontal line intersects the graph in, at most, 1 point. So this might sound very familiar to the vertical line test, right? Where that proves it's a function. This proves it's 1-to-1 for every horizontal line. So let's just graph all these functions. Whoops. Okay, so there we go. So let's graph these functions. So determine whether the function is 1-to-1. So 3x plus 2. So we should know how to graph that now, right? You start at 0, 2. That's the y-intercept. Go up 3, 1, 2, 3 over 1. Go down 3 over 1, down 3 over 1, right? So this is our line. So then the question is, does it pass the horizontal line test? Well, if you look, notice, right, every single time a horizontal line crosses, it's only going to cross at one place. So this is 1-to-1 by the horizontal line test. All right, here's another one. So we got the square root of x plus 2. So we should remember the square root of x equals looks like this, right? So we have the square root of x plus 2. Using our transformations, we can see this means that we're going to move the graph to the left 2 units. So we start at negative 2. So that's our graph, right? And if you notice, once again, it's going to cross that graph in at most one place, right? Down here, it's 0, so that's okay. Any other place is going to only cross it once, so we also see that it's 1-to-1 by the horizontal line test. And then very quickly you can see that part C isn't going to work, right? So remember, x squared starts here and goes up like this, right? So if you subtract 3, that means you go down 3. So transformations, that's why they're super great. So more or less it's going to look like this, and as we can see, right, there's one place that it does not work, right? The line crosses it in 2 places, so it is not 1-to-1 by the horizontal line test because it crosses there 2 places. Cool. And on a test, you can use either one of them to show that it is or is not 1-to-1. You can either use the definition or the algebraic definition, which is what we did, right? Using these formulas, or you can just graph it if you know how to graph it and use the horizontal line test. That also works. So one thing that we also see is that increasing or decreasing functions are one-to-one. So that's exactly what this says, right? So if a function is increasing throughout its entire domain, it's one-to-one. If the function is decreasing throughout its entire domain, it's one-to-one. And we actually see this from the first two examples, right? So in the first example, this is an increasing graph. It goes increasing from negative infinity to positive infinity. It's constantly going up. And we see that since it never stops, never turns, never does anything like that, right? It's just always going up. It's going to be one-to-one. Same thing with the second one, right? Even though it starts at 0, or starts at -2, right? In the domain, it's continually going up afterwards. So that's also one-to-one. All right. Now we can finally talk about inverse functions. So the reason why we had to talk about one-to-one functions is because you can only have an inverse if it's one-to-one. So let f be a one-to-one function with domain D and range R. We say G is going to have a domain of R and range of D. If you notice, those are flipped, right? And we say this is an inverse function of f, provided that these conditions are true for every x in the domain and y in, or x and d and r and y and r. Yeah. So we know that y, all the y's equals f of x, and also all of the x's have to equal g of y. So a reason why it has to be one-to-one, right? So remember, two things. So for a function to work, right? One x cannot be touching two y's, right? That doesn't make any sense. That's not a function. So if we don't have a one-to-one function, right? If we have two x's, oh, am I having some technical difficulties? There we go. Hopefully. Oh, there it is. Okay. So if we have two x's, right, going to the same y, then when you flip that, going in the opposite direction, notice we're not going to have a function anymore, right? G wouldn't be a function because you have a y going to two different x's. So to be able to have functions, right, you need these, or to have inverse functions, you have to have one-to-one, right? One x can touch one y, and one y can touch one x. So that's why one-to-one is important. All right, so the inverse function theorem. So here's a way that we can determine if things are inverse functions. So again, make sure that your function is one-to-one, domain D, range R. If G has them flipped, so the domain is R and the range is D, then we say that G is an inverse function if and only if both of the conditions are true. So if we have G of f of x, what should happen? So if you have x in your domain, right, and it's pointing to some y, so if it goes in this direction for f and it goes back in this direction for g, you should just end up with the same thing, x. Likewise, if we have f of g of y, if y goes to x through g and then back to y through f, when you go through this whole process, you should go back to y. These are called identities. Whatever you start with, after you go through the function, you end up with the exact same thing. It's called an identity function. Cool. Domain and range. So you might have already caught on to this, right? So a notation that we can have is f negative 1. So we could just write that as the inverse instead of saying g every single time. Notice f of negative 1 is not the same as f over, or 1 over f, right? This is just a notation. This notation just means inverse function. So it's definitely not 1 over f. It's not an exponent, right? So this doesn't hold, right? It just means inverse function. So the domain of the inverse function should be, well, let's look at it. So we said in this one, right, the domain was R. What did we see about R in the original function? It was the range. So the domain of the inverse is the range of the original. And likewise, the range of the original is, or the range of the inverse is the domain of the original, which is kind of neat. And this is going to be very important to know for later. All right, so how can we actually make these inverse functions? As soon as we finish with this, we're just going to do a couple more examples and then we'll be done. So first, verify that your function actually is one-to-one. Remember, if it's not one-to-one, we can't even do this, so then we're done. So verify that it is one-to-one. Solve the function f of y for x in terms of y. So what does that mean? What does it mean to have x in terms of y? So remember, it means x equals something with y. And in this case, it's going to be that inverse function is what it's ultimately going to look like. And then essentially, sorry, we should have a step 3, or maybe, so we'll have a step 2.5. So right before we finish, right, you can just switch your x and your y. And you want to make sure to do that after. I know sometimes you might have heard in high school, they say flip it first, flip your x and y's and then solve for y. I'm going to show you why we actually shouldn't do that. We should let we should solve for x first and then switch the x and y to get our function. I'll show you that in a second. All right, but we do need to verify the two conditions. So we got the inverse of f, right? When you plug x into the function and then its inverse, we should get the same thing when it's in the domain of f. And then likewise, when you plug it into the domain of the inverse, you should end up with the same thing. All right, and again, this, you don't have to do this part. This is just to verify, is to make sure that you actually got it right. So yeah, so let's try this one out first. All right, let's let f of x equal 3x minus 5. Find the inverse of f, and then determine the range and domain of the inverse. All right, so step 1, is it one-to-one? We actually see, yes, it is one-to-one, because it's increasing. So we can say one-to-one because it increases, right? We said all increasing functions are going to be one-to-one. So done. All right, number 2. So let's solve x in terms of y. So we have y equals, we can just substitute that out, right? Y equals 3x minus 5, and then solve for x. So we got y plus 5 equals 3x. So x equals y plus 5 divided by 3. So then we can just flip it, right? So we have the inverse function is x plus 5 over 3. And then step 3, we can just verify. So we can have the inverse of f of x, right? So f of x is 3x minus 5. So if we plug that into our original, or into the inverse, we have 3x minus 5 plus 5 over 3. These two cancel, so you're left with 3x over 3, and you got x. Quick switch, and we can see f of x plus 5 over 3. Right, that's going to be 3 times x plus 5 over 3 minus 5. 3's cancel, so we're left with x plus 5 minus 5. Those cancel, we get x. Perfect. So we know we get it. We know we did it right. So now let's just figure out the domain and the range. Well, if we look at this, right, are there any fractions? Well, there are, but notice x is not in the fraction, and that is not in the denominator, which is really what we mean when we say fraction. X has to be in the denominator. That's not the case, so we're good there. There's no even radicals, so we see that the domain of the inverse is just negative infinity to positive infinity. So what about the range of the inverse? Well, that's a little harder to figure out, right? But from our previous theorem, we know that the range of the inverse is the domain of the original. So all we have to do is look at the domain of the original. And again, there's no fractions, no even radicals, so there's no restrictions. So that's just going to be negative infinity to positive infinity again. Cool. All right, let's look at example 4. So this is when things are going to get a little crazier. So let's let f of x be 3x plus 4 over 2x minus 5. Find the inverse and the domain and range. So first thing we got to note, we have to determine that it's 1-to-1. And we haven't talked about this yet. This is a function called a rational function. Typically, you would have seen this if we were going in order, but we don't go in order in this class, so you haven't seen this yet. So you can just assume that any rational function is 1-to-1, and you can say because I said so. Now, that is not, you can't say all functions are 1-to-1 because I said so, right? We know how to do 1-to-1 functions. Either they're increasing or they're, we can do the graph or we can do algebraically, right? So you don't get an excuse on the test to say all functions are 1-to-1. But if you ever see a rational function, you can just say, assume it's 1-to-1 because you said so. That's totally okay. So if it's something like you have an x over x, right? A rational function, rational number, get where that comes from? Yeah, so as long as you have x over x, you can just say, well, you said so, so it's 1-to-1. All right, so now we got to do the inverse. So we have y equals 3x plus 4 over 2x minus 5. And you may notice, because we're going to do another example just like this, that the same steps, this is basically the same steps for every single one. It's just moving some things around. So first things first, fractions suck. Let's get rid of them, right? So we can multiply both sides by 2x minus 5. And when we do that, that cancels out the bottom. We can distribute the y. So we get 2xy minus 5y equals 3x plus 4. Now the whole thing is to isolate x. So we need all the x's on one side, everything else on the other side. So we'll do 2xy minus 3x equals 5y plus 4, right? So we move the 3x to this side, the 5y to that side. All right. Problem still is that we have two x's and we need down to 1x. So one thing we can do is we can factor out the x. So it's x times 2y minus 3 equals 5y plus 4. And then we can just divide it out, right? So x equals 5y plus 4 divided by 2y minus 3. So to actually write that out, when we flip it, we say the inverse function is, and what did we say that was? 5x plus 4 over 2x minus 3. And we could check it, but no. If you want to check, you can verify on your own. These are a little more complicated. It just takes a long time. You don't want to do it. I don't want to do it. It's fine. So let's talk about domain now. So the domain of the inverse. So let's ask ourselves, is there a fraction? Well, actually, yes, there is, right? This is a fraction. So how do we deal with fractions? We have to set the denominator equal to 0. So when we solve for that, we see that x is 2/3, which means that x cannot be 2/3. Are there any even radicals? There's not. So what we have is we'll have negative infinity to 3/2 and 3/2 to positive infinity. That tells us that it is gone. We don't have it anymore. Let's look at the range of our function. So again, that's going to be a little harder. How do you do range? Well, because we know of our setup, we got to look at the domain of f, which is right here. Again, it is a fraction, so we can just look at solving for 2x minus 5 equals 0. Notice that x is going to be 5/2, which means it can't be 5/2 in this case. So the domain is going to, or the range of our inverse function is negative infinity to 5/2 to infinity, and we're done. So that's how we're going to figure out the range, right? It's by looking at the domain of the original. That's the trick to these. And some of the homework assignments, I don't remember, but it may say something like don't find the inverse function. I'll never ask that. You can always find the inverse function if you want, and I would encourage it. It'd be good practice anyway. So even if the homework says don't find the inverse function, go ahead and find that inverse function. All right, let's do another one just to get familiar with it. This is a little crazy. So number one, we're finding the inverse. We can just, since it's a rational function only, we can assume all rational functions are 1-to-1. That's okay. So number two, let's have y equal 2x minus 7 over 9x plus 1. So if you notice, we're actually going to do the exact same steps that we did last time. We're going to multiply by the denominator. Fractions suck, get rid of them. We're going to distribute that y. We're going to move the x's together and everything else away. So 9xy minus 2x equals negative y minus 7. We're going to factor out that x. And then we're going to divide. So x is negative y minus 7 over 9y minus 2. Which means that our final function, our inverse function, when we flip the x and y, it's going to be negative x minus 7 over 9x minus 2. And we can check it if we want, but it's a lot of hassle, so we don't need to worry about it. So let's find the domain of the inverse. So again, we have a rational function, we have a fraction, so we can just set that denominator equal to 0, which means that x is going to be 2/9. So since it can't be 0, we know x can't be 2/9, so it's going to be negative infinity to 2/9 and 2/9 to infinity. Then we got to find the range. So again, remember that's just finding the domain of the original. So since the original has 5x minus x plus 1 in the denominator, we need to solve for 9x plus 1 in the equals 0. We see that x is going to be negative 1/9. So that means the range is negative infinity to negative 1/9, negative 1/9 to infinity. Cool. All right, 2 more examples and we're done. All right, so let's let f of x equal x squared minus 3 for x is greater than or equal to 0. Solve for the inverse. So first, is it 1-to-1? Well, if you remember, an x squared, we said is not 1-to-1, right? Because that means you can have a negative and a positive. However, notice we restricted our domain to just be positive. So if you graph that on just either non-negative, 0 or positive, it's going to look like this. And we can see that this actually does pass the horizontal line test. So it is 1-to-1. But it's because we restricted the domain to be able to make it 1-to-1. So this is actually going to be the example where we don't want to switch x and y first, we want to keep it. So to actually find the function, we solve for x. So we see that it's x squared is y plus 3. So x is plus or minus the square root of y plus 3. Never forget your plus or minus. That's super important. However, what do we know about x? We know that x is greater than or equal to 0. So since x is greater than or equal to 0, we know we're going to use the positive version. And that is why you want to keep all of your variables until the very end when you switch. Because if you had switched this as y, you would have no idea that it needs to be the positive version, right? This easily could have been negative, right? Less than or equal to 0. We still could have done the same problem, right? But because we left it to where x and y, we were solving for x, we notice that this x has to be positive, right? Or 0. So we just left it with the positive version. So that means our function is going to be the square root of x plus 3. Good. I mean, this is an easy one if you want to verify. So we can put, whoops. We can put f of the square root of x plus 3. Right, so that's the square root of x plus 3 squared minus 3, which is just x plus 3 minus 3, which is x. Cool. And if we switch it around, the inverse into x squared minus 3, so we get the square root of x squared minus 3 plus 3. Right, that cancels, so we get the square root of x squared, which is just x. Same thing. So, what is the domain of our inverse function? So, looking at our inverse function, do we have fractions? Nope. Do we have even radicals? Yes, we do. So, this even radical, right, you got to make the inside greater than or equal to 0, which means that x is greater than or equal to negative 3. So the domain of our inverse function is negative 3 to infinity. Now let's look at the range of our inverse. Again, that's the domain of our original. And what was the domain of our original? Well, if we look at this, it seems like it's all real numbers, but remember, we limited the domain to only x's being positive or 0. So we don't even have to do anything. It told us what it was, right? Just going from 0 to infinity, and we're done. Last one, I promise, and we're done after this. I just want us to see a cube function. All right, so number 1, is it 1 to 1? Well, we do know it's 1 to 1. We can graph that, right? So that's increasing, so we know it is 1 to 1. All right, so let's do y equals x cubed. So how do you do this one? Well, just like if it's a square, you take the square root. Since it's cubed, you take the cube root. So we have the inverse function of x is the cube root of x. That's super easy to verify if you want to do that, right? The cube root of x cubed is x, and the cube root of x cubed is x, right? They cancel both ways. Looking at our domain of the inverse, what's our domain? So, are there any fractions? No. Are there any even radicals? No, this is an odd radical, right? So are there any restrictions? No, there is not. Negative infinity to positive infinity. And then what about the range? So remember, the range is going to be, whoops, the domain. Darn it. I don't know what is happening here at the very, very end. It's the domain of our function, looking at x cubed, right? Are there any fractions? No. Are there any even radicals? Nope. So are there any restrictions? No. So once again, that's just going from negative infinity to positive infinity. And we're done. All right, so if you have any questions, let me know. But hopefully that was, hopefully now you understand how to do inverse functions. All right, I'll see y'all next class. Everyone have a great day.